This topic is all about partial fractions, where a complicated fraction term is broken into two or more simple fractions. This becomes very useful when you want to find inverse Z transform, for example, or Laplace transform, or even simplify expressions for calculus, and so on. The easiest way to understand this concept is beginning with an example. Let's start with fx equals to 1 over x squared plus 5x plus 6. The denominator is a quadratic equation, x squared plus 5x plus 6, which can be easily factorized into x plus 2 multiplied by x plus 3. So fx can be rewritten as 1 over x plus 2 multiplied by x plus 3. Now my goal is to break down 1 over x plus 2 multiplied by x plus 3 into much simpler terms as a over x plus 2 plus b over x plus 3. And we now need to find what the value of a and b are. If I were to take the expression from step 3 and recombine it, I would arrive at a multiplied by x plus 3 plus b multiplied by x plus 2 over the complete denominator. And then if I take terms with the same order of x and group them together, I get a plus b multiplied by x as the first term and 3a plus 2b as the second term. The original fraction that I had was 1 over x plus 2 multiplied by x plus 3. The denominators are the same, and the numerators also have to be the same. So therefore, a plus b, which is multiplied by x in my step 4, has to be equal to 0, because the original numerator does not have any terms in x. And 3a plus 2b has to be equal to 1. So now I have two expressions and two unknowns. When I solve them, I get a equals to 1 and b equals to minus 1. So therefore, fx can be written as 1 over x plus 2 minus 1 over x plus 3. Here are some common rules for decomposing fractions. Use the same recombination method as in the previous slide. Compare with the original expression and find the unknown constant. We already solved for this, where you have a quadratic equation that can be simplified into something like 1 over ax plus b multiplied by cx plus d. So the partial fraction decomposition terms would be a divided by ax plus b divided by cx plus d. In the second row, we have 1 over ax plus b to the power m. In that case, the partial fraction decomposition term would be a1 divided by ax plus b plus a2 over ax plus b whole square, and so on until you reach the highest exponent value. So for example, if you had 1 over x plus 2 multiplied by x plus 3 whole square, then the x plus 3 whole square part would be written as a over x plus 3 plus b over x plus 3 whole square. If you have an irreducible quadratic, like in the fourth line, then 1 over ax plus b multiplied by cx squared plus dx plus e can be written as a over ax plus b plus bx plus c. Note the inclusion of an extra term multiplied by x in the numerator. For improper fractions, that is those with a numerator with a higher degree than in the denominator, you have to first divide the numerator by the denominator to reduce the improper fraction to a proper fraction. So for example, if you were to simplify fx equals to x cubed over x squared plus 5, the degree of the numerator is 3 and the degree of the denominator is 2. Therefore, the numerator needs to be divided by the denominator first. And then fx can now be written as x minus 5x over x squared plus 5. Here are more examples of fractions and their decomposition equivalents. So we already looked at one where we had fx equals to 5x over x minus 1 multiplied by x minus 5. So this can be written as a over x minus 1 plus b over x minus 5, and then you find a and b. In 2, we have a repeating factor as x minus 1 whole square multiplied by x minus 5. So this must be written as a over x minus 1 plus b over x minus 1 whole square plus c over x minus 5. In 3, we have the same expression as 2, but instead of x minus 5, we have x squared plus 5, which is an irreducible fraction. So this can be rewritten as a over x minus 1 plus b over x minus 2 whole square as before, plus cx plus d over x squared plus 5. Note the difference between cx plus d over x squared plus 5 and c over x minus 5. We do introduce cx plus d because x squared plus 5 in itself is irreducible. In 4, we look at x squared plus 5 as a repeating term itself. So this entire expression can be rewritten as a over x minus 1 plus b over x minus 1 whole square plus cx plus d over x squared plus 5 plus ex plus f over x squared plus 5 whole square. In 5, I have 1 over x to the power 4 minus 1, which can be factorized into x minus 1 multiplied by x plus 1 multiplied by x squared plus 1. So we applied the same rule as we did to number 3, and we arrived at a over x minus 1 plus b over x plus 1 plus cx plus d over x squared plus 1.